So in this second part of the video, we're going to start talking about the second possible reason that a nuclei could be unstable. And you can see there that it's the ratio of protons to neutrons that make the atom unstable. So remember that the neutrons are there in order to keep the electron repulsion of the protons from being too great. So if you have too many protons, not enough neutrons, too many neutrons, and so forth, you get an unstable situation where the protons could push each other apart, or the strong force isn't good enough. So let's take a look at this scenario. So if there's too many neutrons, this is going to cause a release of a beta particle. Occasionally you'll get a neutron. This is much more rare. Usually it's a beta particle. So you're probably thinking, a beta particle, how do we do that? So we'll get to that momentarily. The other way is you could have too few neutrons, so now you have too many protons. What happens is you cause the release of a positron, which we haven't really talked about yet. Again, we'll get to that as well. Or on occasion a proton. So notice that if there is instability in the proton to neutron ratio, you can get 4 of the possible 6 decays: a beta decay, a neutron decay, a positron decay, or a proton decay. So we're looking at 4 of the 6 decays as being responsible for, or as a result of, this relationship. So let's start with the too many neutrons and talk about the beta particle. So a beta particle, if you remember, is a high energy electron. It's an electron, same mass, same charge, but it's got an extra high amount of energy. So just like we did with the alpha particle, let's look at the isotopic notation. You're going to see that it looks a little different, because normally where the atomic number goes, we're going to put a -1, because the electron is really opposite of a proton, right? The number down here, the atomic number, usually identifies the number of protons. Well, we're going to put a -1 because it's the opposite of a proton. So instead of putting the charge up here when we do nuclear decay, we're going to account for the fact that it's an electron by putting a -1 down here. And electrons have no charge. Notice the beta in the Greek letter is very cursive looking. Again, in class I can show you how to draw it by hand. They are very small and very fast, but they are still reasonably easy to shield. So they're smaller than alpha particles, they're faster than alpha particles, but we can still easily shield it because it is a particle. So particles can't necessarily get through denser materials. And because it's easy to shield, again, its penetrating ability is pretty poor, so that makes it dangerous on the inside of the body. So alpha particles and beta particles are really dangerous inside the body, but not so dangerous on the outside of the body. Again, you wear protective gear, gloves, goggles, and so forth. You can protect yourself from alpha and beta particles. So let's look at a spontaneous beta decay. So here's an example. Radioactive hydrogen, which is called tritium, has 2 neutrons and 1 proton. That's too many neutrons to be stable. So the atom wants to decay. Well, look what it does. It kicks out a beta particle, which is essentially an electron, from the nucleus. What? How can there be an electron in the nucleus? Well, let's look at the daughter isotope, the daughter product. Where there was 1 proton, now there's 2 protons. So think about what we did. We took a neutron, which is neutral, split it apart. We made all the charge of negative to the electron and all the mass and positive charge to the proton. So notice that the mass number didn't change, but the atomic number went up by 1. So this is what's really going on. How do you get a neutron? We're going to an electron out of the nucleus, we're going to split a neutron. So the neutron, with a charge of 0 and a mass of 1, is going to split into a proton, so it gets the positive charge and the mass, and an electron, which gets the negative charge and very little of the mass. If you remember back when we did the PowerPoint about protons, neutrons, and electrons, a neutron weighed a little bit more than a proton. Well, here's how we can get that electron out. Again, notice that the positive charge rose when we went from the radioisotope to the daughter isotope. Positive charge goes up, but the mass doesn't change. So how would you solve this one? What am I going to get? Take a minute, figure it out. Hopefully you figured out that we were going to have same mass number, 147, because the electron coming out, the beta particle doesn't have any mass, but one of the neutrons gets converted to a proton, so our atomic number goes up by 1. Spontaneous neutron decay is pretty simple. Isotopic notation for a neutron, like you saw on the last slide, is 1, 0. So if a neutron gets ejected, again, this is not the more common way. If there are too many neutrons, more likely than not, a neutron is going to split because it gains a proton if that happens. Loses a neutron, gains a proton. Here, we're just losing a neutron. So the element doesn't change, but the isotope of the element changes. This, again, is less common than to have the neutron split to create another proton and a beta particle. All right, so now if we look at the other possible way, what if we have too few neutrons? What's going to happen? So a positron is what's going to be released most commonly. A positron, if you look at it, has the mass of an electron, but it has the charge of a proton, +1 and 0. It is generated when a proton splits into a neutron and a positron. So here's the equation. We take a proton and split it. The proton gives the mass to the neutron, and then the beta particle, or I'm sorry, the positron gets the positive charge. So the neutron has no charge, the positron has no mass. That's how things get split. So here's an example. We take bromine and we lose a positron. What happens? We've lost a proton, so we've gone down 1 on the periodic table, but the mass number stays the same because that proton has been converted to a neutron. So we still have the same amount of mass, but we lost one of the charges. And again, this is the most common thing to happen when you have a higher proton to neutron ratio than is comfortable. So beta particle gets released when you have a high neutron to proton ratio. Positron gets released when you have a high proton to neutron ratio. You could also just have a positron emitted. Again, not a positron, sorry, a proton emitted. Not often going to happen. Again, the positron emission is more likely to happen than a proton decay. But here's an example. Americium is going to lose a proton to become plutonium. So mass number goes down by 1. I'm sorry, atomic number goes down by 1. Mass number goes down by 1 because we've lost a proton. So then we get to reason number 3. You could have a nucleus that is just super high in energy, an excited nucleus. In that case, it's just got a lot of extra energy. Oftentimes, extra energy will be released as a result of another decay. So you can have an alpha decay along with energy being released from that excited nucleus. But when that happens, the energy that's released is going to be in the form of a gamma decay. So if you remember, a gamma ray, not a particle, there's no such thing as a gamma particle, there's no mass. It's just a wave of energy. So when we do the isotopic notation, okay, again, this is gamma. This font is a little misleading. This should be a bigger loop at the bottom. So watch my arrow. It should go kind of like this. So we want a big loop at the bottom. Sometimes I tell kids it's like a fish diving straight down to a deeper depth. So you want a big loop at the bottom. That's a very small loop. But anyway, again, I can show you in class by hand. It's energy. There's no mass. There's no nothing. It's just 0, 0. So this is the case where it's a wave of energy, travels at the speed of light. There's no mass, so it's very light. It's got no mass. As a result, it's very difficult for us to shield ourselves from gamma rays. So if a gamma ray comes through the room, it can pass right through your body. The good thing is it can pass right through your body. So its penetrating ability is excellent, which means it's not going to stick around. So this is kind of the weird thing. If you have radiation treatments, they don't use alpha and beta particles to do radiation treatment. They use gamma rays, because if a gamma ray is pointed at you or released inside the body near a set of cancer cells, the gamma ray will hopefully kill a cancer cell on its way to leaving your body, and then it's gone. So alpha and beta stick around much longer in your body than a gamma does. A gamma can pass right through. So they actually use radioisotopes that give off gamma rays as a way of treating cancer therapy, because the gamma rays are not going to stick around. So the high energy will be used to kill the cancer cells, and then the gamma ray leaves your body. So because there's no mass or charge loss, there's only energy loss, a spontaneous gamma decay is pretty darn easy to write. There's no change in the daughter isotope from the radioactive isotope, because the only thing that's changing is the amount of energy in the nucleus. And we can't show that just by isotopic notation. So I don't even have a practice one for this one because it's pretty darn easy. All right, last slide I want to show you kind of summarizes the ideas that we've been talking about. You have this in your binder in black and white. This one's in color. I have shared with you in the agenda and in Schoology a colored version. So if you would like to print this out in color, be my guest. But notice what we're looking at. Most of the graph looks orange or blue or yellow because those are the three most common decays. Okay, so here's what I want to show you. This straight line here is the 1-to-1 ratio between protons and neutrons. The x-axis is the number of protons, the y-axis is the number of neutrons. When atoms are small, they can have the same number of protons to neutrons. Not a big deal because there's not a whole lot of negative repulsion, or I guess I should say positive repulsion, between the protons. The neutrons are, the few neutrons are enough to keep the few protons apart. But as we get more and more protons, that repulsive force, that electrostatic force, starts to gain traction. So we actually need to add more and more neutrons, and that's what this black stair step is. This black stair step represents the isotopes that are not radioactive for the different elements. Notice that as soon as we hit, about 20, we have to start adding more neutrons in order to keep those protons separated. And as the number of protons gets bigger, we need even more and more neutrons to keep that nucleus stable. On the on either side of this stable staircase are the isotopes that are unstable, the isotopes that are radioactive. So if an element, let's say this element along this area here, here's the stable ratio. If you have too many, or I guess I should go up and down. If you have too many neutrons for that element, it's going to do a beta decay. Too many neutrons are going to convert a neutron to a proton and release a beta particle. That means it's going to be able to drop down. It loses a neutron, gains a proton, so it drops closer to the line. If with that element you have not enough neutrons, the proton is going to split apart, create a positron, and gain a neutron. So again, it's going to move towards that line. So either way, a beta particle or a positron decay is going to move the element closer to that stable staircase. If you have just big atoms, that's where the alpha decays undergo. So notice that there's not really any alpha decays down here because the nuclei are rather small. You get alpha decays when you just have an enormous, when you have an enormous nucleus. What did I just do? I ended the slideshow. Let's go back one. There we go. So you've got a lot of alpha decays when the atoms are just super big. Notice we've got neutron and proton decays. There's just a few of them. Again, if I have too many neutrons, sometimes I'll get a neutron decay. If I have too many protons, sometimes I'll get a proton decay. So notice that that happens more often with the smaller atoms that are radioactive than with the bigger atoms. Don't worry about fission, we'll talk about that later. But the black, again, are the stable non-radioactive nuclei. That's kind of the target ratio. If you don't have that target ratio, this is what's going to happen in order to try and get to that target ratio. So there you have what we're going to talk about as far as nuclear radiation goes.